Hello everyone, I am Karthikeyanas working as Assistant Professor in Department of Chemical Engineering in Karpam Academy of Higher Education, Coimbatore. I am here to present a video lecture series on mechanical operations in chemical engineering, which consists of 8 video lectures with a duration of 10 to 15 minutes each. The lecture 1 will be Introduction to Particles. The lecture 2 will be Properties and Storage of Particles. The lecture 3 will be Size Reduction Operations. The lecture 4 will be Size Reducing Equipments. Lecture 5 will be Solid-Solid Separations. Lecture 6 will be Gas-Solid Separations. Lecture 7 will be Solid-Liquid Separations. Lecture 8 will be Transportation of Solids. Today we are going to see about the lecture 1, Introduction to Particles. Before moving to the particles, we need to know about what is chemical engineering. The chemical engineering is the process of conversion of bulk raw materials into bulk products by the use of unit operations, unit process and chemical reaction engineering in industries. The chemical engineers will design, develop and monitor the complete process. Then they chooses the raw materials, operates the plant safely, efficiently and economically. And also they checks whether the product meets the requirements set by the customer or not. The chemical engineering is a branch of engineering which evolved in late 1890s. The chemical engineering consists of unit operations and unit process. The unit operations is developed by Dr. Arthur D. Little in 1915. The unit process is developed by P.H. Groggins in 1923. The unit operation consists of mechanical operations, fluid flow or momentum transfer, heat transfer and mass transfer. The unit process consists of the chemical process such as nitration, oxidation, hydrogenation, halogenation, hydration, etc. The mechanical operations which we are going to see in this lecture and this lecture series consists of the size reduction operations, handling of solids, processing of solids, transportation of solids, etc. Next we are going to see about the unit operations and unit process. The unit operations and unit process are the integral part of the chemical engineering. The unit operations and unit process are the series of physical and chemical steps which are involved in the chemical reactions which are taking place to convert the raw materials to the products. The series of steps which involves the physical changes are termed as unit operations. The series of steps which involve the chemical changes in the materials under consideration are termed as the unit operations. Unit operations is developed by Dr. Arthur D. Little in 1915 as said earlier. The unit operations is broadly classified into heat transfer, mass transfer, fluid flow or momentum transfer and the mechanical operations which is in the scope of our studies. Next we are going to see about the mechanical operations. Mechanical operations is the unit operations of the chemical engineering. The mechanical operations uses mechanical forces either small or large in the processing of the materials as such or materials present in other solids. Generally, solids are very difficult to handle compared to the other fluids such as liquids and gases. This is because the solids have definite shape and size compared to the liquids and gases. The liquids and gases, they occupy the shape and size of their containers. They don't have their own shape and size and it can be easily transported from one place to another. For example, if you take the liquids and gases, they can be transported from one place to another through pipelines, but we have to decide the means for the solids based on their shape and size. Thus, for a better understanding of the mechanical operations concepts, it is broadly classified into 3 categories. The first one is particulate solids, the second one is particle dynamics and the third one is mixing. The particulate solids consists of the characteristics, handling, size separation and size reduction of the solids. The particle dynamics consists of sedimentation, settlement, filtration, fluidization and elutriation. The third one, that is mixing, consists of mixing of the solids, the cohesive solids and the liquids. The mechanical operations play a major role in all the chemical industries and the minerals and the metallurgical industries as well. Next we are going to see about the particulate solids. The particulate solids handling is very difficult compared to the other liquids and gases. The particulate solids have definite shape and size. Because of this definite shape and size, we need to find the different methods for transportation, storage and handling of the particulate solids. For regular particles like cubes and spheres, we have defined shape and size. For irregular particles, it is not easy to measure the shape and size. So it is important to understand the different properties such as shape and size for all the particulate solids, because this will be useful in improvement of the handling and designing of the process. Next one is properties of solid particles. The solid particles may be of different form, that is cubical, spherical, rectangular, cuboidal, powder, angular form, etc., which may be in hard, soft, ductile, tensile materials, etc. Irrespective of their forms, the particulate solids have definite shape, size and composition has to be studied. The composition will be useful in defining the density and conductivity of the solid. Next, shape and size plays an important role in the particulate solids. The shape and size are well defined for regular particles like sphere and cube, but for irregular particles we cannot measure easily the shape and size. So in order to measuring the shape and size, we need to go for different methods such as microscopic methods and elutriation methods, etc. Then it is important to know how the particles are mixed, how the particles are handled, how the particles are behaving in other fluids, etc. Next we are going to see about the characterization of solids. The characterization of solids consists of three parts. First one is particle shape and size. The second one is mixed particle size. The third one is average particle size. The mixed particle size is used for calculating the particle size present in the mixture. The average particle size is used for the particles present in the uniform mixture. Next we are going to see about the particle shape and size. The particle shape and size are the important characterizations of the particulate solids. The particulate shape and size are calculated for the regular particles such as the sphere and cube with a singular measurement. If we know the diameter of the sphere, we can calculate the surface area and volume of the sphere. If we know the side length of the cube, we can calculate the surface area and volume of the cube. For other regular particles like cylinder and cuboid, we need to know more than one dimension for calculating their surface area and volume. So if we know the diameter and height of the cylinder, we can calculate the surface area and volume of the cylinder. If we know the length, breadth and height of the cuboid, we can calculate the surface and volume of the cuboid. Next we are going to see about the particulate shape. The dimensionless term phi, that is sphericity, is used to compare the irregular particles with that of the sphere. The sphericity is the term developed by Hack and Waddell in 1935. The sphericity compares itself with the sphere of the particle. In another way, we can define the term sphericity as the surface to volume ratio of the sphere having the diameter dp to the surface to volume ratio of the particle having the nominal diameter dp. Sphericity. For the irregular particles, we can calculate sphericity phi is equal to surface to volume ratio of the sphere with the diameter dp divided by the surface to volume ratio of the particle with the nominal diameter dp. That is Sp by Vp of the sphere with diameter dp divided by the Sp by Vp of the particle. That is phi is equal to 6 by dp Vp by Sp of the particle. The sphericity is calculated for variety of shapes. If we consider the sphere, it has the sphericity of 1 because it compares the sphere with the sphere. So it will have the ratio 1. For other particles such as cube, we have 0.81. For hemisphere, we have 0.84. For cone, we have 0.79. And the other three-dimensional particles, that is polyhedron particles, when the sides are increasing, it approaches to the sphericity of 1. The sphericity of different industrial and food grains are as follows. The industrial materials such as silica sand, titanium slag and elementite having the range of 0.5 to 0.8. The food grains such as wheat, chickpea, bulgur, then pulses have the sphericity in the range of 0.01 to 0.001. The sphericity approaches minimum when the irregular shapes deviates more from the sphere. The sphericity approaches maximum when the irregular shapes combine to the sphere. Next we are moving to the volume shape factor. The volume and surface area of the granular particles can be measured by calculating the dp. The dp can be calculated from the screen size or from the electron microscopy. The volume can be calculated by using the volume shape factor A. If we consider the volume formula of the sphere, V is equal to 5 by 6 dp cube. In this we are deriving the relation V is directly proportional to dp cube. So V is equal to A dP cube for other irregular solids, where A is the volume shape factor. For sphere, A is equal to 5/6. For other irregular particles, we are considering the surface shape factor. The surface shape factor is the reciprocal of the sphericity of the irregular particles. Next, we are moving to the size of the particles. The size of the particles is the linear dimension of the particle. The sphere comes as the perfect example for the size of the particle with diameter dp. For the irregular particles, the size of the particles can be found by taking the average of the longest dimension and the shortest dimension, or the second longest dimension. Sometimes it can be represented by nominal or equivalent diameter. Next, we are going to see about the equivalent diameter. The equivalent diameter is considered as the diameter of the spherical particle having the same controlling characteristics of the particle under consideration. The controlling characteristics are the volume, surface area per unit mass, settling velocity, etc., depending upon the systems and process in which the particle is involved. Different ways of expressing the particle sizes are volume diameter, surface diameter, volume to surface ratio diameter, etc. There are 4 types of particles. They are coarse particles, fine particles, very fine particles, and ultra fine particles. The coarse particles are assigned with the units of inches or millimeter. The fine particles are assigned with the units of screen sizes. The very fine particles are assigned with the units of few micrometers or nanometers. The ultra fine particles are assigned with the units of surface area per unit mass. There are different ways of measuring the particle sizes. They are screening, elutriation, sedimentation, electron microscopy, light scattering, laser scattering, photon correlation spectroscopy, etc. Among all the above mentioned techniques, the screening is the most easiest techniques and economical technique, but in screening we can measure up to only 50 micrometers. Next, we are going to see about the mixed particle sizes. For the particles having constant sphericity and density, the specific surface area is represented as 6 by rho v into summation of xi by dpi average, where xi is the mass fraction. The average particle sizes. The average particle sizes are measured for the different controlling characteristics such as volume, surface, mass, volume, and number of particles. The volume mean diameter is expressed as dV is equal to cube root of 1 by summation of xi by dpi cube. The arithmetic mean diameter based on number of particles is expressed as dA is equal to summation of ni by dpi average divided by nt. Nt is the total number of particles. Let's come to the end of this session. I hope you understood the basic concepts of introduction to particles. In this lecture, we have seen what is chemical engineering, what are the unit operations and unit processes. Then we moved into the mechanical operations. In mechanical operations, we have seen the particle sizes and shapes, characteristics of the particles, and we move to the mixture diameter and the arithmetic diameter. In the upcoming lecture series, we are going to discuss about the properties of solids and their storage. Thank you.